So, welcome to the 9th session, and in this session we shall continue to answer the question that we had raised in the previous session. Namely, in the RC circuit that we saw as a real life example to test additivity, homogeneity and shift invariance, what little changes do we need to introduce to make a difference to these properties? So, first of course, let us complete our discussion on the additivity, homogeneity and shift invariance of that circuit. Let us look at that circuit. We had this RC circuit there, and we agreed that the output Yt would be the voltage across the capacitor, and the input would be the input voltage to the circuit. R and C are the resistance and capacitance values respectively. And we had the system description given by x of t is Rc dyt dt plus yt. We had reasoned that the system obeys the principle of superposition, meaning that x1t resulting in y1t and x2t resulting in y2t implies that alpha x1t plus beta x2t results in alpha y1t plus beta y2t for all possible x1, x2, alpha and beta. So, the principle of superposition automatically gave you additivity and homogeneity, and we now need to ask what is it that would destroy this superposition in terms of the circuit behavior or elemental behavior. So, suppose you took the resistance. What little change could you make in the resistance so that this superposition principle is no longer true? Suppose the resistance were non-linear. In other words, suppose instead of the resistance obeying the relationship voltage being proportional to current, there were a tweak of non-linearity there. The voltage is not quite proportional to the current, but to some power of the current. Now, you might wonder why we are considering an example like this in real life. Well, when you go down to microelectronic devices, resistances do behave non-linearly at times. So, if you were to construct an RC like circuit in a small little semiconductor situation, so if you were to construct it in a microelectronic situation, you might have to worry about this. You might have to worry whether the so-called resistor that you have built in an integrated circuit has a linear relationship between the voltage and the current or not. So, in other words, the first situation which destroys superposition is if Vt and It are non-linearly related. For example, suppose Vt is equal to R times some power of It. Let us say It to the power of, let us say, some gamma, and gamma is a positive number. Now, of course, when you write something like this, you have to be careful about interpreting it for negative It. So, for negative It, you would probably need to interpret this to the power of gamma in such a way that it has physical meaning. Whatever it is, when you do something like this, you make the circuit non-linear, and then it destroys the principle of superposition. In fact, there is another situation in which the superposition principle would be destroyed, and that can be done in a very simple physical way. We can essentially evoke what we learnt in the last few discussions, the principle of a DC offset. So, suppose you put a DC offset in this circuit. In other words, you constructed a circuit like this. You have a resistance, you have a capacitance, but then you also have a voltage source here, a DC voltage source. Let us say this voltage source is 2 volts with the polarity as shown, and of course you have the input voltage here, which we have called x of t, or the input x of t with this polarity. And now you have the output voltage, or the output, which is the capacitor voltage plus 2 volts. There is a bit of trouble here now. What is the describing equation? What is the current in the circuit? The current in the circuit is, of course, again C times dVct dt, where Vct is the capacitor voltage. Now, with this, we can write down the total input xt is equal to R times the current plus Vct plus 2 volts, and that is R times C dVct dt plus Vct plus 2. And Vct, as you see it, is Yt minus 2, or in other words, Y of t is Vct plus 2 volts. Therefore, dyt dt is of course equal to dVct dt. That is true. So, interestingly, here you have the relationship xt is Rc dyt dt plus Yt, and this also obeys the principle of superposition. But now write the equation back in terms of Vct. So, here we have continued to obey superposition, because it is the same equation essentially. But now write the equation back in terms of Vct and call Vct as the output. So, in other words, note that xt is equal to Rc dVct dt plus Vct plus 2, and call Vct as Yt now, or Y tilde t, a new output. You have the equation xt is Rc dy tilde t dt plus Y tilde t plus 2. And now you have trouble. You will notice that this is very like that DC offset that we had in our system description. And I leave it to you as an exercise. Let me write that exercise down for you. Show that this system does not obey superposition. Now, let us ask the other question of this system. Is it shift invariant? Let us try to answer the question informally. What would we mean by shift invariance? You would essentially mean that if I shifted the input by a certain shift, let us call it T naught, the output should be shifted by the same shift. Now, look at the system description. Of course, here let us avoid that 2 volts DC offset. So, let us go back to the original system and ask the question first, right? This system, I mean. Remember, if this were xt and yt, the system description, we will just quickly write it again, is xt is Rc dyt dt plus Yt. And then x of t minus t0 is clearly produced by y of t minus t0, because you will realize that dy t minus t0 dt is the same as dy lambda d lambda with lambda substituted by t minus t0. That is not too difficult to see. This is indeed true. That means essentially we are saying that the derivative operator itself is shift invariant. So, because the derivative operator is shift invariant, when I take a derivative, when I take a sum, these two operations together do not destroy shift invariance, and therefore this whole system is shift invariant. Of course, that is not too difficult to see even by looking at common sense explanations. If I were to give a certain voltage pattern to this circuit and look at the output of the capacitor, and if I were to shift that same pattern in time and look at the output of the capacitor again in time, the only change would be that the output of the capacitor would be shifted by the same amount in time. There would be no other change. So, the system is shift invariant. Now, I leave you with a question to be answered. I have that offset system which I have constructed with a voltage source of 2 volts, and I have looked at both cases, taking the output of the capacitor and the source together and taking the output only across the capacitor with the 2 volt source present. Which of these systems is shift invariant? One of them, or both of them, or none of them, and why? I leave you with this question until we meet again in the next session. Thank you.